Hi, and welcome to the UMAP introductory lecture. UMAP stands for Uniform Manifold Approximation and Projection. And since this name probably sounds a bit tricky, let's go on and explain what it means part by part. First, the projection. The UMAP is embedding algorithm. It is the algorithm that aims to project high-dimensional data into low-dimensional space, where a low-dimensional space is usually two-dimensional or three-dimensional. And of course, the algorithm also aims to preserve all the essential relationships and patterns between the data points. Next, we have the approximation. And frequently, it is impossible to preserve all the information from our data while reducing the data dimensionality. And for this reason, this embedding we will obtain is approximation of the original data. The next keyword from the name is manifold. And what manifold is a generalization of the idea of a curve or a surface in a higher dimensional space. So a curve is a manifold in two-dimensional space, surface is a manifold in three-dimensional space, and the generalization of these shapes in four-dimensional, five-dimensional, six-dimensional spaces, these are manifolds. And we have the manifold in the name because the algorithm aims to capture the shape the data is making in this high dimensional space. So, for example, if we had two-dimensional space and we had this data that forms a straight line, so this is the data manifold. This shape is a data manifold in a two-dimensional space. So we want to capture the analogy of this in a higher dimensional space. And finally, we have uniform, which comes from the assumption of UMAP that data is more or less uniformly distributed across this manifold, across this shape it is creating in this high dimensional space. So this was the name. Now let's see how the algorithm is working. Let's see the bigger picture behind the UMAP. So as we have said earlier, UMAP aims to transform n-dimensional data and make it m-dimensional and also preserve as much information from the data as possible. So we will start with n-dimensional data. And the next thing we will do is represent data as a graph. And in this graph, the data points will be nodes. And the edges between the nodes will represent the similarity between the data points. So edges will have weights, and these weights will be higher if data points are close to each other in the feature space. And the way we will construct this graph is by using a nearest neighbors technique. Namely, each data point will be connected to its k nearest neighbors, which are k data points that are closest to our data points in the feature space. So if we had these data points, here is our coordinate system. And if we wanted to create a k nearest neighbors graph with k equals 2, in that case, this data point would only be connected to these two nearest neighbors. And after we perform this step, we have a graph. And this graph represents the relationships between data points from the original dataset. But important difference, important characteristics of a graph is that graph doesn't have characteristics of dimensionality. all we have in a graph are nodes, edges, and edge weights. And since we are able to transform n-dimensional data into a graph, it is pretty logical that we can do the reverse thing. We can represent a graph by using m-dimensional data. So what we will do is start with, for example, 200 dimensions, transform this into a graph, something like this. So nodes and edges, nothing else. And after that, we will aim to transform this graph into two-dimensional or three-dimensional data. So this is the big idea behind the UMAP. And you might be wondering, we already have PCA for dimensionality reduction. Why do we need UMAP? And there are a few reasons. The main ones are UMAP is much better at capturing nonlinear relationships than the PCA, and also UMAP is much better at compressing high-dimensional data into two dimensions, and we want two-dimensional representation in order to visualize the dataset by using regular scatter plots. So this is the main purpose of UMAP. And in this example, our dataset contains this 28 by 28 images, which is 784 features. If we consider each pixel in these images a feature, and we have these images of 0, 1, 2, 3, 4, 5, 6, 7, and 8, and 9. And what UMAP can do in this case is project these 784 dimensions in only two dimensions and almost perfectly separate all of these digits, which is very powerful. However, even though the UMAP is an excellent tool for visualizing high-dimensional data, it is not advisable to use UMAP as an intermediate step in a data science pipeline. For example, it is not advisable to perform the clustering on this embedded data because UMAP can introduce certain distortions in the data, which we will learn about later. So if you want to, for example, cluster the lower dimensional representation of the data, you should run PCA and select the number of components that explain the high percent of variation in the dataset, and only use the UMAP for visualizing this data. And with this out of the way, I want to shed some more light on these two main UMAP steps. I want to enumerate the main sub-steps in order to give you better overview of the UMAP big picture. So as you know, the first step includes transforming original data into a graph. So this step has several sub-steps. So first we must find k nearest neighbors for each data point, and after that our next task is to find similarities between data points and neighbors, and after that we will make these relationships symmetrical, and we will use this to form the weights of the edges in a graph. And after that, we want to transform this graph into two-dimensional space, and we will do this by first assigning random 2D feature values to the data points. So we will represent the dataset by using two features, and each data point will start by having some random values. And after that, we will use stochastic gradient descent in order to optimize these feature values with the goal of having similar relationships in this two-dimensional space like we have in this graph. And all of this is actually based on a complex fuzzy graph theory, but can be explained by using concepts that are a bit simpler. And this is what we will do. So in this course, uh, we will use very basics of fuzzy sets. We will use k-nearest neighbors concepts. We will use basic graph theory that we already have learned, and we will use stochastic gradient descent. And this is it. This wraps up our introductory lecture. So here we have learned what is UMAP, or at least we have gained the high-level perspective, and we have kind of learned about basic building blocks. See you in the next lecture, where we will scratch the very surface of that theory.